Welcome to another Tuesday lecture in GR. We are in the middle still of differential geometry. Today we will make progress towards a more physical view of everything. So we will start to profit from the structure and from all the language that we introduced so far. Let me start answering a question that came up. I didn't have much time actually no time after last lecture to answer questions, but there was something asked later. And also, of course, you can still, maybe after that answer, also ask your questions that you wanted to ask after last lecture and couldn't. But let me just start with the answer to one question that was asked, which somehow concerns the coordinate representation. Last time we have introduced the so-called Lie derivative. Now, generally the derivatives are used in differential geometry to somehow view things in a tangential space. So remember that the actual things on the manifold that we will be interested in are, for example, world lines. These are all space-time points where, for example, a particle or even an observer is during its whole lifetime. Or the other things are flows that we introduced last time. They're also defined on the manifold. However, if I want to understand these objects locally, then it's useful to just go to a tangential space, for example, to one point on the curve and ask what is, for example, the direction of the curve at that point. And we have also seen the notion of an integral curve. This is essentially telling us that if we know the direction of a curve at any point, then we can reconstruct the curve. So in some way, knowing the velocity vector or the direction vector that we have used many times, which is an object in tangential space, is providing us the same information as the path or the curve itself. Now, depending on what we want to do, one or the other objects are more useful. And it turns out that many of the mathematical statements are best phrased within the view in one tangential space. So we kind of look at an infinitesimal part of the curve. That's how you should view that. So it's really still a physical concept. I mean, sometimes one could understand taking differentials and so on as something that is purely mathematical, but its meaning is really to look at the small part of a curve. And if the part is small enough, then the curve in that small interval is just specified by its direction. And the same is now true for flows. There, somehow the Lie derivative that comes from the flow says everything about the flow, if you like. And so for mathematical statements, we will often be interested in the Lie derivatives because they give this treatment, this local treatment. You could also say the tangential space and also the derivatives and all that are somehow the local descriptions that of physics. And we know, or I've told you at the beginning, that the idea, one of the central ideas of general relativity is to go to local inertial frames, or not necessarily inertial, but free-falling coordinate systems or observers. And free falling can only be defined locally. If I'm in a big gravitational field, for example, that of the Earth, then different pieces at different points in space would kind of be, if you still think conventionally of a force, be directed or pulled into different directions. But if you look at things locally, there's one direction. And that's one central idea. And going into these local view is essentially corresponding to the mathematical concept of derivatives. Okay, so this was just to give you again an idea of where we are. We have introduced the Lie derivative. Now the question was, what does the Lie derivative really mean, or how can we represent it in coordinates? I gave at the end of the last lecture, without the proof, a small expression for the Lie derivative in coordinates. But let me expand a bit on that, because the question was, how do we deal with all these concepts once we have introduced coordinates? How do we actually calculate with them? Now, remember the definition of the Lie derivative. didn't involve any coordinate system. It was essentially just saying, take the flow and look at two very close things, I mean, infinitesimally close, and see how they change. And by things, I should say, these are tensors. And so we could now look at the Lie derivative for different rank tensors. For example, the simple thing is a 0,0 tensor. So I would like now to answer this coordinate question by essentially telling you about the Lie derivative in coordinates. And I hope this will somehow also clarify a few other things at the same time. That's why it's a very useful question to ask. You should actually always ask this question if you see a concept, how does it now look like in coordinates? Because that could give you new insights. So if you look at a scalar or a 0,0 tensor, then the Lie derivative is as follows. So f is just a function. So of course a function can be regarded as a 0,0 tensor. Just another way, a fancy way to talk about the function. And the Lie derivative is now something that is defined for a vector field V. As I said in lecture notes, I usually call that X, but just for notational reasons or for to make it distinguishable from coordinates, I call it here V. So we have this vector field V, that's the river in the examples of last week. That's the flow of the river. And we ask ourselves, how does the function change as we flow along the river? And here we have seen, and I just repeat that for a 0,0 tensor, the Lie derivative acts in the natural way like a vector acts, because a vector was already defined as exactly that thing, namely the vector acting on a function tells you how the function changes as you move along a path in the direction of that vector. So in this sense, the Lie derivative of a 0,0 tensor is just the derivative induced by the notion of a vector. And therefore, we already know how it looks like in coordinates, because in coordinates, you know that a vector can be expanded in a basis, and the basis vectors are these objects that look like partial derivatives, but they're not, they're vectors in our way of thinking, and this whole thing acts on F. But now this thing really acts on F in a way we already understand, and maybe just, maybe that's just notation to remind you, because I'm going to use it. This object, which is defined as how does this basis vector act on F, will be sometimes as a shorthand just be written as df to the dxi. So I just put the f on top of the fraction bar, but it really means this thing, the vector acts on f. And you know, the meaning of that is not that it's a partial derivative of f directly, because f is defined on the manifold. It's the partial derivative of f it's a partial derivative of the chart representation of f. You have seen all that, and you can of course go back to the definition of these things. So here we already understand it. So that concludes what I wanted to say about the scalar. But now the more interesting part, and this is also the part I didn't prove last time and will do now while answering this question, is what if we consider a 1,0 tensor, which is of course a vector. So 1,0 tensor is also just again a fancy way to talk about the simpler object, namely a vector. And I want to do that in several steps. So now this is really the calculation I should have done last time. The first step is I just expand the vector in a basis, in a coordinate basis. Because if I want to talk about coordinates, obviously I need somehow. So as soon as I decide that I talk about coordinates, it's useful to expand these things in the natural basis. And let me take here the index j. This is just some summation index to expand this vector W. Now you have to remember a rule that I already told you last time about, namely that if we take the Lie derivative of an object which consists of, here this is a function, times a vector, then something like the product rule applies. So you have to be aware of the fact that this wj is not just a real number. This is not a constant. This wj is a function which is defined everywhere on the manifold. Because, remember, the W itself is a vector field. It's a vector at every point on the manifold. And you can now regard this as a scalar defined at every point of the manifold. So this is itself a function. So it's something like this f. And if I now take the derivative of the whole object with this product, then according to what I already introduced last time, I talked about the properties of the Lie derivative. We first have to apply the Lie derivative to the first factor of the product, which is just the wj, and not to the second one. So the second one is not in the derivative, plus the factor, and then the derivative, the Lie derivative applied to the other part of the product. And this other part is itself a vector, but now it's a simpler vector, it's just a basis vector. Now the next step is, maybe I'll write this here before really writing a step. We have already seen just above how a Lie derivative on a function acts. So we essentially know this is just the same as V applied to wj. And of course, I can again expand this in a basis. So I'm here just applying this for f being wj. And what I get is vi times d to the dxi. So this is the expansion of v, for which I use a different index than j, because j is already used. And then it acts on wj. So this is, by the way, this is where the d to the dxi acts. And then I still have this other factor, which was there, the vector d to the dxj. The second part of the sum, I use something that I also mentioned last time. I mentioned last time that the Lie derivative applied to a vector is just the Lie bracket. So maybe I'll write this briefly. So we already know this is just the Lie bracket of v to the d to the dxj. I didn't prove this, but actually the next exercise will include parts where, or at least parts of that proof. So the Lie bracket is also antisymmetric, so I can write it as minus d to the dxj, comma v. And now I can again write it as a Lie derivative. So I just go backwards and say, now I have essentially exchanged the thing in the subscript with the argument it acts on. So I can regard it as a Lie derivative with respect to the vector field d to the dxj applied to the vector field v. So I can always do that for with Lie derivatives for vectors, exchanging essentially the subscript with the argument the Lie derivative acts on. This is quite useful. And I, of course, get a minus sign here. Now I forgot, okay, actually I shouldn't forget this factor here. So let me put this somewhere. Maybe I just do that set that into a bracket, because the Lie derivative doesn't act on wj, but the wj should, of course, still be there. Now, the next step is to actually try to understand this thing a bit better, but we do that. We already have done this before. So again, what we can do is just to expand the argument v. So if I just rewrite this blue part, I don't want to write the whole line again. The blue part is just the Lie derivative to the vector field d to the dxj applied to vi, and then this whole thing to the d to the dxi. So I just expand v and apply again the product rule, plus vi, and then the Lie derivative applied to the other thing. So actually I need more space here. So let me move this a little bit. Okay, So it's again the same use of the product rule as before, where I expanded v in the basis. So here the derivative d to the exj now acts also on the basis vector d to the dxi. Okay. Let's now see what we can do with that term. There's one thing that is useful, or that you can see when you look at that. Again, a Lie derivative of vector. This is a Lie derivative of vectors, and it can again be written as a Lie bracket. So this is d to the dxj. You see, I go here forth and back. Of course, it's just the same thing. But we have proved already, I think a week ago, or not a week ago, but I think just last Thursday, that the Lie bracket of two basis vector fields, or the two vector fields induced, or that correspond to these basis vectors, is always 0. That's something we already know. So we get a term that is much simpler. We only are left with that term still, and that one, and this thing here goes away. So let us write this a bit more cleanly. So what we get as a final thing, and I will now immediately also introduce, or not introduce, but use a notation we also introduced. I said that instead of writing this partial derivative always explicitly, we can just abbreviate it with a little comma I. So this just means I take the partial derivative of wj to the xi, in this sense of the chart, I mean, I should say the partial derivative of the chart representation of wj to I. And then, okay, maybe I keep that for later, this term, the d to the dxj, and first write the other part. Oh, okay. Let me nevertheless do it in 2 steps, because otherwise it may be confusing. So I write this. Now I have completely taken care of the first term. Now the second term, we just have to write this. But this, again, in components, I mean, there's still the wj we have to multiply to everything. That's this thing here. So we have wj, and then we have the derivative of I to the j. So I again use the same notation. And this is now with respect to the basis vector d to the dxi, not j. Now that's a bit unfortunate that we have a j here and here an I, but I can just relabel things that I'm allowed to do. So you see, whenever you have summation indices in a term, I can relabel them arbitrarily. So I can just change the j's here into i's and the i's into j's. And then I have something nicer, because now I can really bracket out these remaining vectors. So here I write wi, v, j, I, and then the remaining vector is that one. Okay, so now it's a bit a long equation. So what we started with is this thing here. And if you look at here the first term after the equality here on the right-hand side, then you see that it also has this d to the dxj. So what this means is that this part here, the bracket itself, the thing I underline, is just the jth component of the Lie derivative. So in other words, what we can conclude, this is just another way of writing what we just saw, is that the Lie derivative, or the jth component of the Lie derivative, so this bracket that I had, must be equal to the bracket here. And that proves now the expression that I think we had last time at the end of the lecture on the board here. That was exactly this thing. Okay, so now you see how we get the component expression, and you now probably also see what I mean, what I meant when I said before that the component expression, or looking at the things in a tangent space and looking at derivatives, makes things mathematically in a way more tractable, because initially, when we started with the whole thing, we had a flow. So remember, the vector field V is just a representation of a flow. And now we somehow understand the flow locally. Now we understand somehow how does something change under the flow. I will just come back again to this meaning of this, but let me first do one last thing. So we have essentially now taken the Lie derivative of a function, we have taken the Lie derivative of a vector, and of course I could take the Lie derivative of an arbitrary tensor, but one thing which is qualitatively already showing everything is if I take the Lie derivative of a covector, because then an arbitrary tensor is essentially just, as you know, has the same behavior as a tensor product of vectors and covectors. So if you understand how the Lie derivative acts on a covector, on a 0, 0, 1 tensor, then we understand essentially everything about the Lie derivative. So I take this W to be a 0, 1 tensor. Before we had a 1, 0 tensor. Now here the idea is to exploit the fact that we already did a kind of cumbersome calculation right now, and we don't want to redo everything for covectors. And indeed, we don't need to do everything. And this is now a general receipt that will again be useful later, maybe on Thursday, when we consider so-called covariant derivatives. This is a different type of derivative, but the tricks I'm showing here, in particular this like way of getting the behavior for covectors out of the behavior for vectors will be always the same. So the same techniques that I'm showing you now will be useful later again. So please try to pay attention to the general technique, and then the details are something that may be a bit different from when you go from Lie derivatives to so-called covariant derivatives, which we'll learn about still this week, I guess. So the trick is that we use the fact that we can, of course, always apply a covector to a vector. So W, or this omega, so this is actually an omega here. This is not a W. Maybe I should make this more clear. So this is an omega. There are always Greek letters for covectors that I'm trying to use. And so we apply this W to a vector. We apply the omega to a vector W. Now the point is that this object here, omega applied to W, is again just a function. Remember, a covector that eats a vector gives out a value at each point of the manifold. That's a function on the manifold. And so this is just like the F that we had before. So we already know what this does to this object here. So in other words, the left-hand side of this equality, the one I've already written down, is already completely understood. But now we can rewrite it. We can write it as the Lie derivative applied to the trace of omega and W. Now you have to remember what the trace does. The trace applied to such an object does exactly this. It transforms this tensor product into this acting on this. So think of trace, always take the first part of the tensor product and apply it to the second. That's what how we define the trace. I mean, it can be defined more generally, but that's what it does in this particular situation. Now we have already seen properties of the Lie derivative, and one of the properties was that the trace commutes with the Lie derivative. So I can just take it out of the Lie derivative, and what I'm left with is this expression here. Now another property of the Lie derivative is this product rule that we already applied. And in this particular case, the product rule will lead to the following. We apply LV first to W and don't do anything to omega and don't do anything with W. And then we keep the omega and apply the Lie derivative to the W. And the whole thing is in this bracket over which the trace acts. Now we essentially evaluate the trace. The trace will again just say apply this first part to the second. So what we are left with is the Lie derivative of omega applied to W plus omega applied to the Lie derivative of W. Now there's again something we understand. So this, maybe let me point this out. This is a 0, 0 tensor. This is, of course, the 0, 1 tensor we are interested in. So that's kind of this part of the sum is what we are really now want to understand. And this is something we already understand. This is the 1, 0 tensor. This is the vector. And now it's clear if you understand this and this, you immediately have an expression for that just by rewriting this equality here. So let's do that. And let me immediately write the whole thing in components. So I have L, V, W, J. So I'm interested in the J component. Oh, maybe I should write the J downstairs. I'm sorry for that. J, this whole thing is now a covector, 0, 1 tensor, so it has the indices downstairs if I write down the components. Now, what does this mean, the J downstairs? It really means, how do I generally get the J component of a covector? I get it by just applying the covector to one of the basis vectors. That's what we learned. That's essentially what it means to take this component. Just insert this, feed this into the covector. Now the next step is to essentially apply what we just derived above, because we have now such a thing where the W is just this basis vector d to the dxj. So we use this expression, so we write this as this thing here minus that. Let me do it. So I essentially just copy from the earlier slide, replacing W by d to the dxj. And then, of course, because I take the first summoned on the left-hand side, I get a minus. So this will be W applied to, oh, no, sorry, I made a miss. It's a second thing. So this I'm interested in, that's what I already have here. And now I'm taking this on the other side. So I get this W applied to the Lie derivative of d to the dxj. Now we use the fact that we know these expressions. So as I said, this is just the Lie derivative of a function, and we have already done it. So the Lie derivative of a function is just act with v on this function. But what is actually the function? This function here is just the jth component of w. Again, for the same reason as what I said about this component. So we can just write here wj. So this really means apply the vector v to this function wj. And now the second term, what I'm going to do here is to use the coordinate expression we derived here. So I'm now using everything we had above. So you see, okay, first we have a w, and I already changed the sign. There will be a sign change. So this plus comes from this minus. So I write this w here and something in the bracket. And what I need to put into the bracket is this thing here. But this, I know component-wise, is what was written here. But the w is now just the vector d to the dxj. So obviously, this just means the component wj is just, or the component of w is just the delta function. So if I have, if I just put here the function d to the dxj, or the vector field, then this whole term here gets 0, because the derivative of w is just 0. It's a constant coefficient I have in front of the d to the dxj. So what remains is this thing here. So again, with the w just being the delta function. So what I end up with. And now you see the minus here, by the way. So the minus here, that, okay, the wrong pen. The minus that you see here, and this minus cancel and give the plus. So let me write this down. I get therefore V J, I. And you see here we had actually a V. Here's a Vj, I. Now, okay, the indices don't match. I'm sorry for that. So I need a new summation index. So this W here is the thing that will correspond to the J I've introduced here. So I need to just put wherever I have an I, a J, and therefore I need to a different index for what is upstairs. So what I get is VI, so that's a new summation index. I could have named it whatever I like, and then to the J, and then D to the DXI. So maybe, okay, if that was confusing, the better, or another way to see it is just look at this part here. And I essentially copied this in the special case where the WI is just 1 if I is equal to J and 0 otherwise. And then you get exactly this expression here. Okay. Then this I can write in components again. You now know how this works. So I mean, I could have first made a step where I write VI to the part and then the partial derivative, but this partial derivative is now denoted by this comma, and then plus. Now this W here that I have acts on something with a vector d to the dxi, but we know that if I act with W on d to the dxi, I just get the i's component of W, and by linearity I can take this out of the argument. So what I end up with is V I, J, W I. Okay, that was a very long calculation, but it's probably worth it because these Lie derivatives will appear very often. And that essentially is a very long answer to a very important question. It took us half an hour, but anyway, needed to go through parts of that. So to conclude, we have now expressions for the Lie derivative of scalars, vectors, and covectors. And there's now one observation I would like you to make aware of. And the observation is maybe best illustrated if you go back to the vectors. So for the vectors, for the Lie derivative, we obtained this expression here. Now compare this to the expression you are used to if you take a derivative just in Euclidean space, in normal or in Cartesian coordinates. If you take a derivative in Cartesian coordinates along a vector along a direction v of another vector field w, then obviously you have to take the derivative of w to the different components. So if you go in direction I, you take the derivative in the i's direction, and then you sum over all directions with the corresponding weights. So this first term really corresponds to what you would do if you take the derivative with respect to a certain direction in normal Cartesian coordinates. However, in the Lie expression, or the Lie derivative, you have this second expression. And this is an expression which takes into account that the direction in which we take the derivative somehow may itself, or the field in which you take the derivative may change itself. So let me relate that to the example I gave you last time. We had the river, and maybe remember this picture I had. I'm lying on a nice boat on a river which floats, and the river is described, the flow of the river is described by V. And then there is the sky, and on the sky I see wind directions. So suppose I could attach little arrows on the sky which shows me everywhere what the wind direction is. Now, as the boat floats, if the river was completely uniformly flowing, every point in the river would kind of flow in the same direction with the same speed, then of course I wouldn't have a contribution here, because this VI simply doesn't change if I go in a direction I. It's always the same flow of the river. So I only have this expression, and this expression really corresponds to how does the wind direction change as I move along the direction VI. This second term is now taking into account that if I don't have a uniform river, but a river which has little turbulences, maybe the boat kind of turns a bit, this is all taken into account by this thing, because if the boat turns, then from my perspective, there's a change in W. So recall that this thing is really how does W change from my point of view, from the boat's, from a passenger of the boat's viewpoint. And so we get these two directions explicitly. That's what essentially this thing tells you. Now, we didn't have these two expressions in the derivative of a scalar, but here indeed, if the boat turns, for example, and if I look at the sky and just see a scalar field, I had this example of just the color of the sky, which may be different. There's different darkness or different tone of blue. Here it doesn't matter if the boat turns around or so, it just changes as I move along. So we have just the term how F changes as I go in a certain direction. And we get this second term because now we are looking at the vector, no longer scalar, and somehow the term here takes into account the change of the reference, the turning of the boat. And the same is true for a covector, which also has a kind of direction. It's just that somehow here we have a plus sign in it's almost the same expression, except that we have here a plus sign instead of a minus sign. And we will encounter that later again for covariant derivatives, that the only kind of, or the major difference between how covectors and vectors are derived, or how you take derivatives, is that there's this different sign. But that's just a small outlook and maybe something to make you aware of the fact that we will encounter that again later. Okay, that's now all. With that, I would like to more or less finish this chapter on Lie derivatives and move on to something which, as I announced, will make the connection to physics a bit more, let's say, concrete in some way. It's still very abstract, but we will add a new element. It's now a good time to ask questions about this whole previous chapter, about Lie derivatives, about flows, about calculations I did. Are there any questions? Okay, this doesn't seem to be the case. So then let me just continue, and you can, of course, at any time interrupt me. The new section is called Affine Connections. Okay, now you may wonder what this has to do with physics, because it doesn't obviously sound like a physics topic. But let me start with an actual kind of thought experiment. So suppose you are in free space, and remember that so far we haven't given any structure to space and space-time except for a topology. So the topology itself doesn't allow you, for example, to talk about or to compare directions at different points in space-time. I mean, we have now introduced the flows and so on, but the flows are just relative directions. So we had to introduce a lot of structure, like if you have a river somewhere or some flow in space, we can kind of compare how one flow changes if I look at it from the viewpoint of another flow. But now forget about the flows. Just ask yourself the following question. I'm starting, let's say here where I stand, and I move in a certain direction, and I want to kind of keep the direction of something that I have in my hand. So I always have this arrow here, that you may remember. So I have this arrow, and now I could say, I tell to myself that I want to keep this arrow exactly, or I want not to change the direction, but walk to another place. So I walk, let's say, to a faraway place, maybe Geneva. And the question is, how can I even express that this arrow still points in the same direction? What does this mean? Because, of course, as I told you many times, the tangent space in Geneva is a different space than the one here. So what does this mean? How can I express that mathematically? Now, physically, this has a meaning, and the thought experiment is the following. I could actually take a gyroscope, and the gyroscope makes sure that somehow the direction is maintained. So I could say, instead of taking this arrow, I take a gyroscope, and I just walk with this gyroscope to Geneva. And now I could again ask, how does this gyroscope, how has it changed directions? But this is actually now a bad question from, let's say, the philosophy of space-time physics viewpoint. You should rather think of it in the following way. You should say the gyroscope defines what it means not to change the direction. So in other words, you just say, I do this experiment to actually find out what it means to not change direction. So if someone asks me, is this arrow, let's say, here in the German part of Switzerland, pointing in the same direction as the one in Geneva, then I would answer the question as follows. We can test it physically. I take a gyroscope, orient it along this arrow here, and walk to Geneva and check whether the gyroscope also points in the same direction as the arrow in Geneva. And if the answer is yes, then I would say, yes, these arrows have the same direction. But this was now not a mathematical definition. It was a direct physics experiment, which tells me what it means that two arrows at different points in space point in the same direction. So the idea now is that we don't try to kind of say the manifold somehow tells us how these directions, which directions are the same. It's rather the opposite. Physics tells us what directions are the same. And what we need to do, therefore, is to impose that physics element onto the manifold. So we will essentially say we have now a new experimental thing we can do, namely follow directions as we walk. And we now put that as an additional structure onto the manifold, onto the space-time manifold. So far, space-time manifold was just a set of points, essentially, with this topological structure. Now we say we equip it with an element that tells us which directions are still the same. So the point that I would like to make is that this is not something that is already there in the manifold. We really impose it. We take essentially data, we take physics data to define it. And so the question whether a gyroscope changes its direction or not has the answer, no, it doesn't change, but not because of a physical law. It doesn't change by definition because it's this very experiment that defines what it means to keep the direction. And somebody needs to say what it means. And in empty space, you have no reference. So this experiment tells you what it means. There is now, however, a difficulty. And this difficulty will make the whole thing actually interesting. Now, I was talking about space-time physics, but to see the difficulty, it's actually, again, good to go back to a simpler case, namely the Earth surface. Already on the Earth surface, I could ask the question, how can I keep a direction? And now, of course, you know the Earth surface is round. And if I walk, let's say if I point this arrow towards you and I walk now for a very long time, a very, very long time, maybe I end up somewhere in Southern Europe. Now, if I would keep the direction straight in three-dimensional space, the arrow would probably slightly point upwards. As I walk, it would start to point upwards. Because if someone would look from the outside, this is kind of what it means to keep the direction. However, I could also ask the question, what if I restrict myself to always keep the arrow horizontal, but otherwise don't change the direction? So technically, this would mean whenever it points slightly upwards, I kind of project it down onto the surface and take the arrow again in that horizontal direction. Okay, and now I can do this experiment. I can walk for a long time and see, and by that define what it means to have the same direction. But now you will encounter that this is not well defined, or maybe to be more precise, it's only well defined if I keep track of the path. And let me just explain that before the break. It's just 1 more minute. So let's suppose I start from the North Pole. So let me now go to the North Pole. So I have here a little curve in front of me. So I'm standing here on the North Pole. So that's where I have the arrow. And now let's suppose I start walking towards the south. Okay, and let me start from the North Pole up to the equator. There's actually not much there in the equator, but I could imagine I walk there. If I, yes, okay, I don't walk everything, but I go there. Then let's suppose I decide to actually move now, to move along the equator. So I first walk to the equator and then I walk towards the east. So when I go towards the east, at some point, I arrive at Malaysia. And now you see the arrow still points now into the direction of the South Pole. I mean, I started here, and let's suppose the direction initially of the arrow was towards the south, but this is not well defined because everything is south if I look from the North Pole. But let's suppose the arrow points towards the south, or towards the direction I need to walk if I want to go towards the South Pole, passing through Zurich on the way. So this is now a well-defined direction. Now I walk like that, the arrow points south. Now I walk left, and I keep the direction of the arrow. I don't follow the arrow, I just keep the direction of the arrow. The arrow is just a gyroscope or so. And now I'm in Malaysia, the arrow still points southwards. However, I could have done something different. I could again have started with the arrow pointing here towards Zurich from the North Pole, but I could have directly walked towards Malaysia. This would look like this. So the arrow now still points towards you and not southwards. So if I now define what it means to have the same direction in Malaysia as the one on the North Pole, then I don't get a unique definition, because if I now do the experiment walking through, first through Zurich and then towards the east, I would say, the arrow pointing southwards is the same as the one that I had here, because I always took it straight with me and never changed its direction. But if I walked this way, I would have arrived at a different statement. I would have said, no, actually, the arrow pointing west is the one that corresponds to the direction I had here. Okay, so the point of all that, of this little thought experiment, or real experiment, if you like, is that defining kind of what it means to keep something in the same direction from one place to the other depends on the path I'm taking as I go from one place to the other. And that will also be the case for space-time. So that's, of course, now obviously true for the surface of the Earth, as I explained, but it will also be true for space-time. But it is exactly one of the consequences of the space-time being curved, because obviously this thing here is curved. If it was flat, if I did the same experiment just on a flat space, then everything would be completely independent of the path. So when we talk about curved space-time, what we mean experimentally is somehow exactly that. You take a gyroscope and go to a different location in space-time via two different paths, but you will see that the result will not agree. Depending on the path, you will end up with different directions. So that's the whole essence of talking about curvature on a qualitative level. Now we want to quantify everything, and this will, of course, or will require some techniques. And the technique we will need to introduce are these affine connections. So that's the topic for after the break. Okay, let me therefore make a small or medium-sized break until 5, and then continue with that section. I'll stay here, of course, as usual, and take questions if there are any.
Yeah, there were a couple of questions in the chat.
Yes.
And one of them was about your example with the river and the flow. And okay, the very first question was, if the vector field is seen as a 1-0 tensor, and if yes, how does the example work? and I think the thing is it's not exactly clear whether V is just a vector field or if it goes with the, how does it connect with the field with the flow. I guess.
So in the case of the tensor, or okay, I may not have fully understood the question. So can you repeat it again?
Maybe, I don't know whether Dario is still there. Maybe he can unmute himself and ask properly the question, because I'm not sure.
It was like the vector field is like a function from C infinity M to C infinity M. But you also said it is a 1-0 tensor. So I don't know how this connection works, that this is a 1-0 tensor.
Okay. Now understand. So your connection between what I said when I said a vector field is a 1-0 tensor and directly talking, or a 1-0 tensor field and talking about a vector field. So yes, that's a very important thing to let's say clarify. So I hope that was the question. So I sometimes okay, we have two notions. We have the notion of a vector field, and then we have also the notion of a 1-0 tensor. Of course, I meant now also tensor field in that way. So let me call the vector field here V, and then the tensor field T. Of course, the point is they will essentially be the same objects, but in what sense are they the same objects? So a vector field, okay, I mean, in both cases, the way you should think of it intuitively is that it's an object that assigns to every point of the manifold a vector. Now, you know that a vector at any point takes as an argument the function and gives out a value, a real value. So I could therefore define a vector field, or one can define them in that way, to say that it takes a function. And now if it was just at one point, so let me maybe first do that. So what we did before was just to consider vectors at a particular point, and then they would map a function to a real value. So f is a function, so this is an element, let me write this is an element of C infinity M, and it maps it to a real value called V of f. V of f. So this is now a Vp of f in this case. So that's now just a, maybe I should write more clearly, Vp of f, that's now an element of R. Now for a vector field, because a vector field is defined everywhere, it makes sense to say it's now doing that at any point. So it defines a new function, Vf. So the left-hand side is still the same. So it acts on a function on the manifold, but it now produces again a function on the manifold. And what is this function? This function is just defined by essentially this thing here. So formally this means that if I take this function and evaluate it at the point P, it's defined to be the vector field P, the vector P applied at F. So that's how we define the vector field. Now, for a tensor field, we have this kind of duality thing. So let me maybe first recall what it is in this particular case. So a tensor field now is something that takes a covector field. So before I had a covector field was something like omega. So that's an element of this thing. So these are covector fields. By the way, V is now a vector field. So that was the notation for a vector field. So it takes a covector field and makes out of the covector field a function. So this is now just for a 1-0 tensor, of course, that's not generally true. It makes, it evaluates this covector field. And now this, what comes out here is essentially, again, a function, C infinity M. Yes, okay. Now, this function is not, okay, maybe I should briefly go back to the reason why already for a point a 1-0 tensor is actually a vector, because that's not immediate. So let me briefly look at that. So if I now look at the thing at one point, Tp, so that's a tensor at one point, a 0-1 tensor. What does a 0-1 tensor do at one point? It takes a covector at that point, let me call it omega p, and makes out of this a number. So that's what a 1-0 tensor does. So that's a real number. Now, why can I say that such an object here, this function, why is this now interpreted as a vector? And okay, the short answer would be to say something that takes a covector and maps it to a number is again the dual of the covector. This is this is an element of the covector field. That's element of Tm at point P. And now if I have again a function on this thing that maps to real numbers, it's again the dual of that. So in principle, this object here would be T star star Pm. But then I said this is essentially isomorphic to Tpm. So we said that the dual of the dual is again isomorphic to the space itself. Now you should really think of this thing as this corresponds to a vector vector field in terms of the same duality relation. Namely, you can just think of this object. This is, if I evaluate it at the point P, corresponds to this. So if I go from this and this to a particular point, I'm here. So in other words, at every point, in some way, maybe the best explanation is to say this thing here, if I look what it means at every point, is exactly this object here, but we already know that at every point, this object here corresponds just to an element of the vector space. So that's a bit complicated because we are somehow doing a detour. We are somehow defining vectors in terms of a function that eats covectors. And the detour is really via this double duality. And the reason why this is done is just that this allows for a simple generalization. If you only wanted to define 1-0 tensor fields, we would just never do it and just directly talk about vector fields. So 1-0 tensor field is kind of a detour to define that, and the detour is exactly via this relation, which is only useful once you have the fully general thing. I hope this helps a bit, but what you should be aware of is maybe that at the end, it's isomorphic to this expression or to this thing here. So try to understand it pointwise, and pointwise, we already have treated it earlier very explicitly. Now for the non-pointwise thing, I didn't explicitly do it, and that's why it's good you asked this question, but you can really, again, just go back to the pointwise thing. So instead of thinking in these terms, just go back to one point, and then it should be clear why it corresponds to a vector at that point. Does this help somehow? Okay, I haven't now heard an answer, but is there maybe an answer in the chat? Loris, do you see anything? So, okay, so that was my answer to the question. I'm happy to come back to the question again, maybe after the lecture, in case the answer wasn't satisfactory. Maybe for those who just joined, I can maybe just give a summary of that question and answer. So the question was, why is actually a 1-0 tensor field corresponding to a vector field? And maybe the summary of the answer is, try to understand it pointwise. So try to again remember that a 0 or whatever tensor field corresponds to being a tensor at every point on the manifold. And we have already treated that case. So we already know that a 1-0 tensor at the point of the manifold corresponds to a vector at that point. And so that's the way you can see that a 1-0 tensor field, the way we defined it, corresponds to a vector field. But please complain if you want to hear more details about that. I could also kind of maybe in the next lecture give a, let's say, full argument for that case, which doesn't reduce it to the pointwise thing. Are there any follow-up questions to that subject?
I would have another question, but it's not very related to the previous one.
Please.
Okay. So it's about how we now like kind of represent vector fields and covector fields in a sense in a basis with a chart. So I'm just a bit worried about what happens. So because the chart is only defined on an open subset of the manifold, right?
Yes.
So I'm a bit worried what happens with this representation if we are at some like where the chart ends to be defined, whether we should worry about that or not.
Yeah, that's really an excellent question. And the short answer is yes, we should worry about it. We haven't worried about it, but we should. And the more detailed answer, which is really I should give, because that's really an important question, is maybe to just give the context, we said that these objects here form a basis of, they are a basis of TPM. Now one could expect that d to the dx as a vector field, now not restricted to one point, but to the whole, let's say, open subset on which the corresponding chart is defined. So remember, of course, I can only define it on the open subset on which the chart map X is defined, is not, so there are several reasons why it's not a basis of, so this is now not necessarily a basis of TPM, because simply it's restricted to U. So this U is the chart map, which is only, or U is the small region or the open region on which I define the chart. So it cannot be a basis of that. Now you could ask, can I somehow extend it to a basis? Or was that
there shouldn't be a P, right? On the
oh, sorry, yes.
Yeah.
I should write here, I wanted to write of TM. So it's not. Now the question is, could we somehow hope to still construct somehow a basis by putting together, I mean, okay, maybe I need a small picture. So if you have here the manifold, as usual, and we have, let's say, one chart here, X, and then we have maybe another chart region or chart map Y, and this is maybe U, and this is V. And now we could say, okay, I have at least here a base, this d to the dx defines kind of a part of the basis for Tm that is valid on this region, and then I just go to the other chart map here, and maybe by cleverly combining them, I obtain a basis of the whole space. Now it turns out the whole space, Tm, isn't even a vector space. And that's actually, it lacks one of the basic properties that makes it having a basis. So the answer is essentially there is even, I mean, this in particular is no basis, but this space in general doesn't even have a basis. it's not even a vector space. And actually a simple example is again, actually this one here. So that's the surface of the Earth. If you ask yourself, is there a vector field on the Earth? Is there a basis vector field that you can define? Then you will see that this doesn't work. And this has to do with the theorem that you cannot essentially, you cannot find, yeah, okay, maybe I just do it specifically. Suppose you actually start somewhere with a basis vector field. So you say, start with Switzerland and put a coordinate system, a chart, which has the east-west direction, so the horizontal one and the vertical one. And now we have the corresponding vector in this direction here. I mean, in the west-east direction and the north-south directions. And they form kind of a nice basis of every region. But now at the North Pole, or somewhere where I put these things together, the things don't really match. So it turns out that if I want to continue these vector fields on the whole sphere, I will necessarily at some point need a vector field that, or at some point the value of the vector field will be zero necessarily. So I cannot have a smooth vector field in all directions such that it's never zero but covers the whole surface of the Earth. Okay, there's this thing I don't know whether this also exists in English, but one says in German that man kann einen Igel nicht kämmen. So it means at the end, if it would actually be abstracted as a sphere, you couldn't put the hair down in such a way that you never get a, I don't know the English expression for Scheitel, but you always would get a Scheitel. And that's the part where the vector field disappears. And the mathematical consequence of that is really that this thing here doesn't have a basis. So nevertheless, in a small region, so as long as we restrict to U, then everything is fine and we can again treat it as a basis of TU. So the statement is actually correct somehow if I put the U, but not globally. So locally I can think of these as basis vectors, and that will be sufficient for almost everything we do, because all the calculations will always take place locally. Of course, we have to be careful when we generalize statements to globally, but as long as we keep in mind that there is this difficulty, and as long as we work with local charts, we can still use that intuition. Okay, that was a long answer. I hope it answers your question.
Yeah, thanks.
Okay. Now affine connections. Okay, that was not the picture for the affine connections. I erase it again. But it's, you remember the Tilde experiment that I just showed you before. And now we turn this into essentially a mathematical definition. So what I told you before, this data that you would get. So let's suppose you do these type of experiments. You just take a gyroscope and walk in, or an arrow or something, and walk in different directions and try to keep the direction straight and see what you can learn from that. Then you get essentially, for each possible path you can take on the Earth's surface, you get a different direction at the destination place that you arrive. And so the mathematical object that somehow summarizes all this data, or that includes all this data, is a priori a rather complex object. And this object is the affine connection. So definition, an affine connection, or sometimes just called connection, associates, so it to any curve, so it's depending on a curve, to any curve gamma on M, a family so there's so it's really a complicated object. For each curve, it's still a family of maps. So, and the family has two parameters, two real parameters, which I call U and T. And each member of the family is itself a linear map. Okay, that sounds incredibly complicated, but you will see it exactly captured what I told you before in this example of walking with arrows around. So think of having fixed the path, and think of now kind of T and U as the starting time or parameter of your path. And so T is the starting parameter. It's on this curve, the parameter T where you start, and U is where you end. And then you get a map, which is the map which goes from the tangent space, the space of directions at your starting point, to the space of direction at your destination point. That's what the whole thing does. So in other words, it takes a vector defined at the starting point and maps it to a vector V. This is a different vector, and the difference is just in where it is. And of course, a vector at a different place is in particular also a different vector. So it takes a vector here to here. So to make the link very explicit to the experiment before, this would be the vector at the North Pole that I had. So I take a vector at the North Pole, I walk along a path, so T is the start point, I end up at time U in Malaysia in this example, and this is the vector it points to in Malaysia. Obviously this map, how the final vector looks like, depends on the path. That's what I tried to illustrate before. So it's inherently depending on the map. Now the definition is not done. We are not done yet with the definition. There is this map have to satisfy certain properties. So it's really a long definition. I apologize for that. I mean, okay, I shouldn't apologize for definitions, but it's just somehow unusually long for a mathematical definition, but you will see it really captures exactly this physical intuition that, of course, for example, the property here says if it just don't move, then obviously the arrow stays. I mean, that's a property. It shouldn't change. Gyroscope shouldn't change if I don't even move in space-time. So it means I'm just looking at it twice at the same point. And in space-time, which really means it's exactly the same arrow. Then if I combine times, so if I first, as I did, walk, so T is the time where I'm at the North Pole, U when I'm somewhere in the south, but have not yet the path eastwards, and then this is the second part, from U to V I would go eastwards. Then this is of course the same as if I would do the map from VT. So it just means that if I had the arrow here on the top, and now first look at the mapping of how is the arrow here on the North Pole mapped to the one here somewhere in the south, and then the mapping, how are arrows mapped here in the south to the ones here in Malaysia. Then the concatenation of this is of course the map that corresponds to the path where I really walk here and then to the left. So that must be the case, otherwise this whole experiment doesn't make sense. And okay, the third thing is an even more complicated condition, but this is, you should just think of it as a continuity condition. So it somehow tells you that the arrow doesn't abruptly change its direction. And this is expressed in the following way. So one has to go to a chart, unfortunately, to express that. So for any chart, Ux, so a chart is now, of course, in a small region. So we're just talking about a change as I walk a very small distance. For any chart, there exist coefficient functions. And these are things that you will see now very often. These are called gammas. So these gammas will now be our friends for the rest of this lecture almost, these gammas on U. So these are functions, but there are many functions. So because these are indices, so in space-time, these are all 4-valued indices. So this is 4 times 4 times 4. So I have essentially 64 functions here on U, such that the following holds. If I look at an okay, let me first just write down the mathematical expression and then tell you why it should be true. So we look at the derivative of this map, of this arrow map in components. So by these components, I mean the usual thing when we look at components. I mean, to extract the i's component, I have to apply the covector dxi at the point where the map maps to. That's the final destination, gamma u. And then this is the map, tau gamma ut. And the other index, j, correspond to what arrow I started with at gamma t. So in other words, these coefficients tell you an arrow in this direction, how much did it at the end point in this direction when it arrived at the destination. And now the idea is that this is given by these coefficient functions, I, j, k, which can be different at any point of the curve, but it only depends on the starting point. Oh, sorry, I made a mistake. I should take here the derivative to u. I'm sorry for that. This should be u, and I evaluate at u equal t. This is just, so I keep the starting point, but I look at the destination point, which is very close to the starting point, essentially in the limit, and I ask myself, how much does the arrow change if I just walk a very small distance? And now, this definition allows that there is still a change. So essentially the definition allows me to say, even this map, the arrow could change even if I walk just one step. But the change should only depend then on the direction in which I walk and not on any other properties of the path. And this is encapsulated by saying on the right-hand side, there's no longer the gamma appearing. You see, on the left-hand side, I have the gamma, the whole path. And on the right-hand side, I only have the velocity or the direction vector of gamma at the point where I start. Okay. So by the way, this thing here, we often use the abbreviation gamma dot k at t. This is just an abbreviation that I will often use for the direction vector of the curve gamma at the point, at the parameter time t. Okay, that's the definition. So it's a whole page or more than a page for the definition. Okay, we'll put it up here. And this is such an important definition that I want to, again, briefly at least give some motivation. So the map tells you how things change. And now these things have probably been obvious. So it doesn't change if I don't move at all. It has this composition of paths, which is probably pretty obvious if you think of the example that we want to require that. And this thing, this last thing, tells you that there may be changes even if I walk very small distances. So this thing can change as I just increase the u. It could immediately get a positive map or a non-zero map or a non-identity map. So this map may change if I start walking, which means that the arrow could immediately start turning as I walk. But the way it turns only depends on the direction in which I walk and not on anything else. Because I mean, that's generally the idea that if I look at the very small part of a curve, the only relevant thing of the curve is the direction of the curve. Now, of course, there's another thing that is encoded here, namely that it linearly depends on the direction of the curve. This is justified by the following observation. Think of reparametrizing the curve. If you reparameterize the curve, I mean, u is, for example, a parameter of the curve. I said this is the curve parameter at the destination. If you reparameterize, then this derivative, let's suppose you reparameterize by a factor of 2. Then this derivative here will result in a factor of 2 as you reparameterize, because, of course, if you change the variables to the new reparameterized one, you get this derivative of the new to the old one, so you get the factor. But the same factor will appear here, because remember that the v, the velocity, it's even more obvious from this expression, is also a derivative to the curve parameter. So the same reparameterization factor will appear on the right and on the left-hand side. If there was a nonlinear dependence, for example, a square dependence here, then the reparameterization of the curve would change the right-hand side, but not the left-hand side, which would mean that the whole thing also depends on how I parameterize the curve. But this expression, therefore, somehow also includes, if you want, this requirement that the curve parameterization shouldn't be relevant for this map. It's only really where I walk to and in which path I take, but not how fast I walk in this example. Okay. So this is probably hard to digest, this definition, but I introduced the definition in that way because it really corresponds to the physical motivation. Usually affine connections are defined in a different way, and we will of course see that different definition essentially in the form of a lemma, which says this definition I just introduced is equivalent to something else. But my approach to this whole lecture is to start always with the physical notions, and you see this is really an experiment you could do to map out space-time. So if you want to understand the curvature of space-time, if you really want to see, is it really curved, you would do it exactly in that way. You would put, I mean, of course, maybe experimentally other methods as well, but one way to do it is to take gyroscopes, move into different directions of space, and then at the end compare them again when you arrived at, I mean, you at the end up in the same point. You arrange the experiment so that you can again compare them, and then you will see that depending on the path, they have different directions. And this will be essentially then this object here. So what these gyroscopes show you will be essentially instances of this map tau. And from that you could reconstruct these coefficients. And these coefficients will contain all information you need to know about the curvature of space-time. So in other words, this experiment with the gyroscopes I just explained essentially allows you to gain all the geometrical information that we need, maybe up to scaling, so we'll come to that. But essentially, almost everything can be derived from that experiment. So this is really the point where physics comes in. Now you see we have not just imposed a structure. We haven't just said space is a vector space. We have really said, no, let's do an experiment and let's take into account that the experiment could result in having here different arrows, and then we get this very complicated structure. But as we will see, this structure is something that is mathematically, again, the same as the curvature of the Earth surface, for example. It's the same type of object. It's a manifold with connection, with things. So let's say if I do it on Earth, this affine connection that I would get by just walking around would essentially contain all information at the end about the fact that the Earth is indeed a sphere. That's all then in these coefficients. Okay, are there questions about this definition? Or about anything that I said before the definition that may be relevant here? Okay, if this is not the case, then let me continue with a remark. The remark is just something that will be useful later for technical reasons. So there's one thing that immediately follows from the definition, namely that if I take the map and go from U to T and then from along the same path again from T to U. So the right argument, the second is always the starting point and the left the endpoint, then of course that's just a map again from t to t, which again by the defining properties is the identity map. Now if I take the derivative of this thing on both sides, of course the derivative to the, or let's take the derivative to the time. Of course the derivative of the right hand side is 0, so I turn things around. The derivative of the left hand side can be evaluated by the product rule, or yeah, it's essentially a kind of, yeah, okay, I'm not sure you call it product rule in this case. It's maybe the rule that you get by applying the normal differentiation rules to a situation where an argument t appears twice. Then it's like in the product rule, you first derive this thing and don't change the rest, and then the rest. So it is a product rule in the sense that this composition is a composition on the level of linear maps. So I think it is really the normal product rule. And what you get, just for matrices, if you like, and what you get is you first apply the differentiation to the first factor of the product. So let me write this down, tau gamma t u. So it's only applied to this. To make sure this is really only applied to this, I put this into brackets, and then tau gamma ut. And then there's of course the second part, t gamma t, tau gamma tu, and then the part with the differential d to the dt, tau gamma ut. Now we can, if you want, evaluate everything at the point t equal to u. So I just put here this thing and say, I want t to be equal to u, here as well, t equal u, here as well, t equal u. Of course, if it's true in general that this whole thing is 0, then it's in particular true at the point where t is equal to u. Now, one observation is that if I set t equal u, then this thing here will again just be the identity, and this thing here as well. So now we have a nice expression that 0 is just this plus this, which means that if I change the order of the arguments, I just get a minus sign. This is very intuitive. I mean, it's kind of clear that if I walk in the other direction, I get a minus sign, but we will need that for our technical argument. In particular, what it actually means is the following. If I now take the derivative of tau gamma ut I j at t equal u. Now, look at this expression that I just wrote and compare it to the defining expression. Then I've here exchanged t and u. Here is a derivative with respect to u, whereas here I have a derivative with respect to t. But what this expression just told me is that this just changes the sign. So I can now just copy the thing on the right-hand side, if you like, and without the minus sign. So you may have asked, why is there a minus sign here? This is, of course, just a convention. But indeed, if I exchange the arguments, then I get rid of the minus sign, and I just have this thing, I, j, k. Now I made t equal to u, so I have to write everything in terms of u in this case, and then gamma dot k u. Okay, that's easy to see. You just plug it into the definition and make sure you don't confuse t's and u's, and then you get that expression. So it's this thing. Now there is one last thing I want to do today, which is quite, I would say, tedious, but we have to do it at some point. This is to see how these coefficients, these gammas, actually transform. Because note that the definition is really very explicitly depending on the choice of a coordinate system. We said that here we choose a chart, and for a chart there exist these little gammas or big gammas. And of course, they may be different for different charts. And I mean, they are different for different charts. And it will be important to understand how they transform. And now, in general relativity, I mean, it's really an extremely nice and beautiful theory. The concepts are extremely clean. The calculations are sometimes quite tedious. This is still not a tedious one compared to what one has to do if one really considers more realistic situations and all that. But already small things become quite cumbersome to calculate. But we have to go through that particular calculation. Of course, it's a purely mechanical thing. So you can program a computer to do what I'm now doing, but it's, I mean, the same way as it was useful to at some point learn how to add numbers, it's also useful to do that once by hand, and then later you can use Mathematica and all that once you know what's going on in the background, so to speak. So let's look at the transformed map. So with this tau tilde, I mean that we take another chart, which I call the tilde chart. So usually I call the chart X and Y, but now for the purpose of this calculation, it's more useful to just call the chart X tilde. And now represent this definition, or this tau that appears in the definition in the tilde chart. So what does it mean? I just insert the definition of what tau was. So remember that I wrote this down here below. So that was what I meant by tau ij. It's this expression. But now, of course, I write it down for the tilde chart. So this is a dx tilde I. And this dx tilde I is evaluated at gamma u. It's actually important to keep this track of where it's evaluated. Then I apply really the map tau to a vector d to the dx tilde j at the point gamma t, at the starting point. Okay, I should write here a bit more cleanly. Let me create some space here. Oops. Okay, so here this is evaluated at gamma t. Now I haven't done anything. I've just copied the definition for the tilde basis, but we know how a basis transformation works. So we know how this can be expressed in the non-tilde basis. We have done these basis transformations. And so you probably remember that we can keep track of how these basis transformations work by just making sure the indices are in a way consistent. So there's an I upstairs with a tilde. So the transformation has to have an I upstairs with a tilde, and then I have to input some summation index with the old basis dx, and I call this summation index q. Then comes just the map that I had already from the beginning on, u, t, and I apply the map now to d to the dx. Now I want to also here put the non-tilde thing, so I introduce another summation index, which I call r. And now, of course, I have to put again a factor that transforms this d to the dxr to the d to the dx tilde j. And here the factor is the opposite, because it's now a vector, not a covector, and it transforms like this. So this is all stuff we learned already. We did these things explicitly. You know how vectors and covectors transform. And that object here is what we before called tau gamma u t q r. I mean, that's just what I now wrote down is again this thing here. I just used this with q and r. So now we know how the tau can be transformed, but we don't want to transform the tau, we want to transform the gammas. So we have to work much more. And that's maybe the last thing I can do really today. After that, I'm getting tired of doing these transformations, but let's do at least that. So what's the gamma tilde? So the gamma tilde by definition is the thing that has the property. So look at again on the previous slides, what it does, it's defined essentially via this. It is the thing that, oh, okay, now let's immediately already use our expression here. So here we have an expression for gamma. Let me just use that one. So gamma ijk, and of course this thing is true even if I put tildes. I just have to put the tildes everywhere, also on the left-hand side. So if I multiply gamma with the small gamma tilde dot kt, now I have everything here on the right-hand side. Then this should be equal to, okay, maybe I put here for completeness, I will have need t equal u. Then this should be d to the dt. Now I just copy the left-hand side of that with the tilde stuff, tau tilde, u t I j evaluated at t equal u. Okay, so again, I didn't do much except for copying this expression. Now the real work starts, because now we have to evaluate this derivative here. I mean, we now essentially do the derivative by inserting into tau tilde this whole expression here, this big thing here, and see what comes out of that. Okay, so let's do that. So the first thing is something that doesn't depend on t at all. That's this thing here. So let's just copy it. Here I have dx tilde I dxq. At gamma u. And then we have...
I'm sorry, can I interrupt?
Yes, sure, yes.
I'm kind of lost when you were trying to write down this tilde. You said we use the map, also the definition before for t ij, right? You write this is dxi on the, and then here you write t gamma ut, and then the d to dxj. And here we have t tilde. So my question is why we don't put the tilde after on the right hand side.
Why we don't do a tilde on the right hand side? Okay, let's
see. Tilde. Yes, it's exactly the first line.
The first line you now see. This line here.
Yes.
Okay, let me see whether I can identify it. So here, this is the line you're talking about.
Yes.
And the question is, why is there no tilde here?
Yes.
Okay, yes. So the answer is that this object here is still independent of a basis. So that's just essentially the map that tells you how I go from TP to TP. So you see, when you look at the definition here on the right-hand side, we started actually without talking about any basis. We just said there's this map tau, and this tau tells you how the direction of the arrow changes. How the direction changes is abstractly really a map that I can talk about without coordinates. Of course, if I want to tell you what exactly is this map, it's useful to have a basis, but the map itself is defined without. And then only by actually multiplying or applying the map to some basis vector, and here applying the dual vector again on the outcome of that, I get a basis dependent expression. So it's a bit similar to, maybe just to make this analogy, and I hope this helps as an analogy, we said a vector can be written in different bases. For example, we can write it as d to the dxi, or we can write the same vector as tilde d to the dxi tilde. Now you see, on the left-hand side, I always have the vector. The vector is really, I mean, keep this in mind. The vector is just the arrow. It has no basis. This thing on the right-hand side, these are now coefficients with respect to a basis. So here it's relevant whether I put a tilde or not. So maybe the notation is not optimal. Some people do a notation like follows. They say, let's here always write in brackets what the chart map is. And then the expression would actually look like this, that you have here the tilde chart map. And that may be somehow a cleaner way of notating it. But let's say the bottom line is really that the objects themselves are not basis dependent, and that's why I don't put tildes there. Does this help you? Or, I mean, if you look at this, this is really still the inside is kind of the basis independent map. Okay, I hope it clarifies. Otherwise, please keep insisting.
Okay. Okay, I can look a bit closer.
Okay, yes. I mean, we can still discuss it later if it's unclear, but this is a general, let's say, thing you should keep in mind, that there are these basis independent objects where we never put tildes or everything, and then we have the basis dependent coefficients of them, and there we only make this distinction between tilde or not. And yes, so let me continue with the calculation. If I take the, so we're still about to take this time derivative here, and if I take the time derivative, you see that I have a t dependence actually here in this expression and here. Now, this again is a product rule, so I will get two coefficients. Let me first just take the derivative of this part in the first sum, and here and not of that part. So I first write just the part I don't take the derivative of, which is the d to the dx r to the dx tilde j. Okay, that was not very visible. I think this was an xr. So I've now just taken that term here and essentially copied it. I'm not taking a derivative, but I take the derivative of the other term, namely of that, or of that one here. So the derivative of that term is tau gamma ut. This has no tilde, this qr thing, and I evaluate this still everything at t equal u. But now we have the second term. So for the second term, I still have this prefactor that remains the same, because this prefactor was not depending on t at all. And now I have to derive this thing here, that thing, to t. So let me write this d to the dt of dxr of dx tilde j gamma t. So the derivative only acts on this, that's why I put brackets here. And according to the product rule, it doesn't act on the other part. So this now just remains underived, p equal u. Okay, now a few observations about this whole thing. So this expression here, for t equal u is just, again, an identity, and an identity in components just means delta qr. So that is the first property we have of the tau maps. Then this thing here is, so what does it mean? You have here a curve along which you evaluate this. This is essentially a function. So you evaluate a function along a curve. But we know already what that means. To evaluate the function at the curve means that we apply the velocity vector of the function to the velocity vector of the curve to the function. So this is really just the same thing. And this we can write in components. So instead of having the velocity vector, I told you before, there is this writing gamma dot, which is just the writing for a velocity vector. And now I need to put the basis, d to the dx tilde k, and then dxr dx tilde j. Okay, so you see this part was just rewritten as does it this in this expansion using the notation we introduced. That's really just a vector in the direction of the curve. Okay. Now, maybe one last step is needed. Let me, for that step, also take care of this thing here. So that's also an important thing. Let me put here a little symbol and evaluate this. So what is this triangle? This triangle is, this is, now we go backwards. We know via the defining property or via this property here that we can again write this in terms of the lambdas, of the gammas. So in terms of the gammas, this means gamma q. So the derivative, okay, I think I made a mistake. The derivative here of the time of tau is by definition equal to these little gamma symbols, rs, and then the velocity vector of the curve and u. Now I want to write this in terms of the tilde vector. So I copy everything, rs, but write here gamma tilde dot s at the point u. But of course, if I change the basis to tilde, I need to somehow put here a basis transformation. So I write here dx. Okay, let me write here instead of s a new index, let's say k. Yes, I think k is a good new index to sum over, and then dx tilde k. So this is a very long calculation, but it's maybe something you should just sit down and go through it again, and then you will see that these are all valid steps. So now we have transformed all the terms and can now, okay, I'm a bit over time, but I just need to write now one last expression where I summarize all we have now done into one nice, or at least a bit nicer expression. So we have first of all the dx tilde I to the dxq. That was the first part of our calculation. Evaluated at gamma u, that's the first factor. Then the second factor, just copy it from above, dxr to the dx tilde j, gamma, actually because I said u equal t, I can now put here gamma u, and then the orange stuff, but orange stuff includes an expression of dxs to the dx tilde k, again at the point gamma u, and then finally the big gamma symbol qrs, and there's also a velocity vector gamma tilde dot k that remains. And now the second term, that was the first one, plus, it's again the prefactor, dx tilde I to the dxq. Okay, that is not very readable. Let me write it again. I on the top and q on the bottom. Evaluated at gamma u, it's the same factor as before. And here we have now a derivative of this. So I just use an abbreviation, namely, as I can write this as a second derivative of dx q. I write here immediately q instead of an r because we have here this delta function to the dx tilde j dx tilde k, and everything evaluated at gamma u, and then gamma tilde dot k. Okay, now we are done. So what have we seen? you see on the right-hand side, there is always this gamma dot tilde. So we can, for the moment, forget about the tilde, just take it out on both sides. It also appeared here above. So if I just encircle the stuff without the gamma dot tilde k, then we have essentially shown that this red box is equal to the red box here. And that's really the transformation rule for gamma. So let me make it a bit smaller that you see it. So what we have is the gamma tilde, ijk, are given in terms of the gamma without the tilde, in terms of this expression. Okay, now let me just make one remark which is important, and then we will discuss that at length next or after tomorrow. What we learn from this is that these gammas cannot be understood as the coefficients of a tensor. Why not? Remember how a tensor would transform. A tensor would transform exactly according to this thing, this first part. You would just put these factors in front, and that was the transformation rule of a 1-2 tensor. So if you would think, because of the indices here, that this is just a 1-2 tensor, or these are the components of a 1-2 tensor, you would just transform it according to the first line, and you wouldn't include the second line. So the important point that you really should never forget in this lecture is that these gammas are not the coefficients of a tensor. This will be very important, and we will discuss what that implies next time. Okay, that's it for today. So that was a long calculation. I will not do all these long calculations in the lecture in the future, but this was one that is so important that I think in a GR course one has to do it once. You will probably see the importance only later, but it's really an important expression. It's one, although it's complicated, I mean, this looks a bit complicated, but it's one that you should somehow memorize. It's really kind of useful if you later know whenever you see such a gamma symbol, oh, this transforms like this. And actually, it's not too hard to memorize because that's just a rule for a general tensor, and then you have to somehow add to your memory. It should already include the transformation rules for tensor. You should add to your memory this additional expression here. Okay, that's it for today. See you on Thursday.